My name is Tom Tecco. I'm Vice President of Automated Analysis Corporation. The lecture that we're going to be discussing now is about finite element analysis examples. The two examples to be discussed are the normal modes analysis of a vehicle interior, and the second example is a muffler example using the finite element method to calculate the pressures inside the muffler. The first example we're going to be doing is a normal modes analysis of a vehicle interior. The vehicle interior is comprised of a rigid walled surfaces in the approximate outline of a full-size automobile cavity. We're going to be assuming rigid boundaries, which mean that the glass and steel making up the body are considered to be inflexible, having zero velocity boundary conditions. We're going to be discussing next the physical modeling and the finite element modeling of the interior cavity. For the physical modeling, we're going to be using linear elastic theory to represent the finite elements within the car cavity. The passenger compartment, as I mentioned previously, is a closed box with reflecting walls. That means that there's no acoustical materials that would absorb sound on the boundaries. The speed of sound is 343 meters per second, and density of air is 1.21 kilograms per meter cubed. This type of representation with the finite element model assumes that the material properties are uniform throughout the fluid medium. The finite element model consists of hexahedral elements with pentrahedral elements used to fill in the more difficult to model corners. Next, I'm going to be discussing the solution procedure for carrying out the analysis. In this analysis, we will be using SDRC ideas for preparing the finite element model of the vehicle interior, and we will be outputting the data from ideas in a Nastran format so that it can be inputted into COMET Acoustics. So the procedure is, after creation of the finite element mesh within ideas, you output those elements in an MSC Nastran format that can be easily read into COMET Vision so that you can create the acoustic data set and prepare the data to be executed in COMET Acoustics. This figure shows a side view or cross-section of the automobile, where this is the windshield and this is an outline of the front seat of the vehicle, and this is an outline of the rear seat of the vehicle. In this particular analysis, we're assuming that the seats are rigid. Of course, in real automobiles, the seats are not rigid, and they can be represented by the material properties if you wish to model the seats with elements. Alternately, you could use a boundary element approach for modeling the interior. In that approach, you could make a multi-zone analysis with different material properties for each zone of the model. This would allow for easier modeling and still allow you to represent the material properties of the fluid and also for the seat materials. Additionally, if you are doing a real automobile, you might want to strongly consider including the trunk cavity in the model, because in the modern design of cars you'll find that in many cases that there is not a rigid barrier between the rear seat and the trunk cavity. As I discussed in the last slide, we could do either a finite element analysis or a boundary element analysis depending upon the types of results we're looking at. We're going to continue with the finite element analysis example. These two views are views of the automobile cavity that was meshed. this being a top view of the cavity and this being an oblique view of the cavity. You notice that this is the front seat outline and the rear seat outline is here. The trunk cavity is not included in this simplified analysis. And of course the shape of the cavity is simplified from that of a real automobile. Now that we've completed the analysis using COMET, we're going to take a look at the results of the normal modes analysis. We calculated the first 5 modes. The first mode being a rigid body mode or constant pressure mode, and it occurs at 0 Hertz. There's only one constant pressure mode because of the scalar nature of the problem we're solving. The second mode at 53 Hertz, you will see in more detail later, is a fore-aft mode, and the third mode is at 87.2 Hertz. It's a side-to-side mode within the vehicle. Mode number 4 is at 102 Hertz and goes diagonally from the corners of the vehicle. And the fifth mode is at 109 Hertz and is called a second fore-aft mode. As you remember, the finite element model was meshed in SDRC ideas, and the acoustical analysis was performed with COMET. Now we're going to be viewing the results of the normal modes analysis using COMET Vision. COMET Vision allows you to do complete graphical post-processing of acoustical data and quantities, as you'll see when we go through these examples. This is a colored diagram showing the results of the second mode, which was the fore-aft mode shape for the cavity that occurred at 53 Hertz. To get oriented, you can see that this would be the windshield area up here. This would be the outline of the front seat, and this would be the outline of the rear seat. In the next slide, I'm going to explain to you the significance of the color fringes shown in the plot here. In this slide, we're going to try to interpret the results that we calculated from our previous analysis. We're going to be looking at the second mode, that's 53 Hertz. The mode shape is shown in color using the capabilities of COMET Vision. So all the post-processing that takes place now is being done in COMET Vision, including the cutting planes, which allow us to look at the interior space of the cavity. Now, one of the things that we wanted to take a look at is what the meaning is of the color fringes that show up in this plot. The different colors represent different pressure levels. Red being a very high positive pressure, blue being a high negative pressure for this particular plot, and green being zero pressure. Now, because of the sinusoidal nature of the pressure fluctuation, the pressure in the front part of the cavity will fluctuate between positive and negative values. Likewise, the pressure in the rear part of the cavity will fluctuate between the negative and positive values. You'll notice that these magnitudes are not equal. This is due to the lack of symmetry for this cavity in the fore-aft direction. Another interesting thing to take a look at is what the influence of this mode could be on a passenger or driver sitting in the vehicle. For a passenger sitting in the vehicle, if this acoustic mode were to be excited, the driver's head would be in a relatively low pressure area at all times. Conversely, if you were a passenger in the rear seat, you would be subjected to fairly high acoustic pressures from this 53 Hertz mode if this mode were to get excited. Now let's talk about the mode being excited. When we did the calculations for the normal modes, we assumed that we had rigid wall or rigid boundary conditions on the exterior surfaces. And this is a good assumption for calculating the normal modes. However, if we were to introduce a flexible panel someplace on the vehicle where there would be some structural velocity caused by vibration, say from the engine or from the road, that vibration could set the fluid in motion on the interior of the vehicle. Now, if the structural vibration is high in the footwell of the vehicle, it would couple very easily with this mode and cause this type of acoustic pressure distribution to take place on the interior. If the roof were vibrating in the center section here, then that vibration would couple very poorly with this acoustic mode, and the chance of it being strongly excited would be greatly reduced. We're going to be looking at the third mode next. This is a side-to-side acoustical mode within the interior cavity. You notice that there are high pressure areas along the left side of the vehicle and along the right side of the vehicle. This mode occurs at 87.2 Hertz and could be excited due to engine excitation. As an example, if you think about a running engine causing the shell of the vehicle to vibrate and causing the side walls, the doors or side windows to vibrate, it could easily excite this mode that occurs in a side-to-side direction. The zero pressure line is right through the center of the vehicle, and you notice that this mode is very symmetric due to the geometry. Also, you'll notice that it's very difficult for either the passengers, or either the drivers or passengers to escape the high pressure areas from this mode. The mode that we're going to be looking at next is the fourth mode of vibration for the acoustic space. You notice that this is a diagonal mode. Again, we have the outline of the vehicle, this being the front seat outline, this being the rear seat outline. And you can see that the high pressure areas are located in the front right-hand corner, the rear left-hand corner, and diagonally in the rear right-hand corner and the front left-hand corner. The areas of low acoustical pressure are through the center of the vehicle longitudinally and through the center of the vehicle laterally. The last mode that we're going to take a look at is the fifth acoustical mode of the interior cavity, and it's a higher order mode. This mode occurs at 109 Hertz, and you'll notice that there are two nodal planes that go through the acoustic space. The green area here is a zero pressure area, and the green area here is a zero pressure area. This is a second fore-aft mode with the high pressure areas at the very back. There again in the center, in the blue areas, and then also in the front of the footwell. We just completed the first example, which was the normal modes analysis of an acoustic interior car space. The normal modes analysis is useful for getting an idea of problem frequencies that could occur in the lower frequency range. The assumptions involved are that the walls are rigid during the analysis and also that it is a fully enclosed space. Normally this type of analysis is used as a first pass in order to get an assessment of the acoustical characteristics of the interior space, and then it's followed by a more detailed analysis that would be a forced frequency response. We're going to be discussing forced frequency response now, but we're going to change to a muffler example as opposed to the interior of an automobile space. Our problem will be that of a simple muffler that has two chambers. In some of the following slides, you'll be able to see where these chambers are located. We're going to be calculating the pressure distribution within the muffler at 500 Hertz due to a unit velocity input at the inlet of the muffler, and we're going to use a rho C boundary condition at the outlet that represents something close to an anechoic termination. This is a calculation that can be used in muffler design to help calculate things such as the transmission loss of the muffler. The transmission loss of a muffler is a difference between the sound power inputted to the muffler and the sound power at the exit when the termination is an anechoic termination. There are many other problems that are of interest in mufflers also, and they can be done using COMET acoustics. For example, one of the other things that's of interest to muffler designers is the noise radiated off of the shell of the muffler. This is important not only for interior noise, but for exterior noise of the vehicle. This type of problem could be solved using the boundary element method in COMET acoustics. Other things of importance to the muffler designer are back pressure. That is, it's the pressure that has an influence on the engine performance. And of course, in muffler designs, you want to minimize the back pressure in the muffler while maximizing the acoustical performance or the transmission loss across the muffler. Now we're going to be talking about the physical modeling and the finite element modeling of the muffler. We're assuming that the muffler shell is made of metal, and for the case of this simplified analysis, we're going to be using a rigid wall muffler with zero velocity boundary conditions around the exterior shell. You'll also notice that this is a two-chamber muffler, and it's divided here and here, and these walls are rigid, and the gas is allowed to pass through this tube opening from the front chamber to the rear chamber. This model was created in SDRC Ideas, and the finite element mesh was then outputted as a universal file so that it could be brought into COMET Vision. In COMET Vision then, we will be applying the boundary conditions and setting up the analysis to run within COMET Acoustics so that we can get the results. In this figure, we're going to take a look at the mesh created for the interior volume of the muffler cavity. You'll notice that the cavity was meshed with hexahedral elements. It's a fairly simple mesh, and in this case we're treating the fluid as having a single homogeneous property. With the finite element method, it is possible to give different material properties to each element or layers of elements within the muffler cavity. This would allow you to account for the change in speed of sound and density of the fluid as the temperature changed through the muffler. Now we're going to review the solution procedure for the muffler problem. We've divided it into 10 steps. The first step in the process is to create the finite element model of the acoustic cavity of the muffler within SDRC Ideas. This could be done in other meshing packages as well, such as Patran and HyperMesh and ANSYS, because the data can be easily imported into COMET Vision. These data files that are imported in the COMET Vision then can be viewed, and you can save the desired view. So the process would be to bring the model in. You can view the model, set up the views that you're interested in, such as side views, front views, oblique views, and store those away later to be used when you do manipulation with respect to boundary condition applications. So after you save your views, and of course you can define views at any time during the process, but normally it's convenient at the beginning to define 3 or 4 common views that will be used throughout the process. But after the views are defined, you can go on to applying boundary conditions, but it's first easy to create groups for the boundary condition application. These are done by different types of Boolean operations and using the mouse to select certain areas on the screen and create groups of elements or groups of nodes. Next, we apply the velocity and impedance boundary conditions to the selected groups from step 4. And then also we assign material properties to the fluid, and these material properties can also be assigned to different groups that have been created. For instance, in this case, you may take a group that contains all of the elements and assign the material properties of air. Step 7 involves setting up the analysis parameters. Whether you want to run a frequency response or a normal modes response can be decided at this step. The last step then is to have COMET Vision write out a COMET Acoustics input data deck, then run COMET Acoustics. Running COMET Acoustics will use the input data file created from COMET Vision, and upon termination of the COMET Acoustics run, you will have an output file that you can then post-process. One of the advantages of doing it in this manner allows you to separate the data input deck from the actual program that runs the software, allowing you the ability to easily edit an ASCII data file of the input data deck, and again the output data is in a ASCII file that allows editing if necessary for special post-processing. But of course all the post-processing can be completed within COMET Vision, working off the standard COMET Acoustics format. In this slide, we're going to take a look at the application of the boundary conditions to our model. You notice that we have a side view of the muffler, this being the inlet end, this being the exit end. On the inlet, we're going to apply a uniform velocity across this inlet surface. And on the exit end, we're going to apply a rho C boundary condition, which is fairly equivalent to an anechoic termination. Now we're going to be looking at the results of our analysis. We did a frequency response at 500 Hertz for the muffler. On the right-hand side of the slide, you'll see the dB scale for the acoustic pressures on the interior of the muffler. The red color corresponding to approximately 87 dB at the inlet of the muffler, and at the outlet with the anechoic termination we have a green color that corresponds to a dB level somewhere around 57 to 51 dB. Now you notice that there are actually places of lower acoustic pressure within the muffler. We've only made a calculation for one single frequency, 500 Hertz. Typically, if you're assessing the transmission loss of a muffler, you'll make multiple calculations at different frequencies and plot them up over the entire frequency spectrum from 0 up to, say, 500 hertz. Now, one of the things that's interesting about muffler design is that you don't necessarily always want all of the tones in the muffler to be low. Different combinations of the tonal quality of the muffler make up the sound that the listener hears, and this can be perceived to be either the sound of a luxury car or of a sporty car. So by using sound quality measurements of the tonal qualities, the analyst can get a better assessment as to the sound of the exhaust system and how it's going to be perceived by the end listener.